Thank you so much for inviting me. It is a tall order to be the presentation immediately following Edward's presentation, but I'll try my best to not sound terrible in comparison. But what I'm going to present today is our work towards a paper that mostly took place when I visited Edward's group, starting all the way back from fall of 2020. And there are many talented co-authors that contributed tremendously to this. But in the interest of the time, I'm just gonna go ahead and dive in to the talk. So the first thing, before getting into what I'm going to talk about mainly, just a little bit of a background about me. As Professor Sirjani mentioned, I am currently a PhD candidate at UT Dallas, and depending on who you ask, I've either already graduated or graduating in May. I'm not sure. But what I'm really looking forward to is joining Edward's group as a postdoc in May. And a brief background about my research during my PhD studies. I've tried to categorize my research into three broad categories. One being on timing predictable, energy efficient, and accurate deep neural networks. And I've tried to sort of depict these constraints on a ternary plot on the right. And the high-level idea is that you would want to be able to find a balance between these constraints in your system. And we found that for deep neural networks in particular, this is a challenge that was not at the time being addressed by existing solutions. And the main motivating example for that research was autonomous vehicles, and we used NVIDIA's platform, latest embedded platforms at the time for our experimentations. And there multiple papers came out of that work, but there is one here published in Usenix ATC called New OS, if you want to give that a read. But I've also done research on timing predictable data management. But what I'm going to talk about today is this third category, which is my work on the deterministic middleware for cyber-physical systems, particularly a subcategory of cyber-physical systems, which we call autonomous embedded systems. So with that, let's kind of get into it. So the reason that we thought this particular aspect of cyber-physical systems, middlewares, would be interesting is that we noticed a very dominant trend in modern cyber-physical systems, in that they're mostly nowadays using distributed architectures. And here I try to depict an abstract architecture for an autonomous vehicle. And you can see there are various ECUs and other types of compute units that are connected via Ethernet or a canvas. And examples of these middlewares in existing frameworks include the robot operating system, which is prevalent in robotics and autonomous vehicles. But there are also many other frameworks and standards, such as ROS, MQTT, and so on and so forth. So the question that we had, especially coming from the realm of lingua franca and deterministic models of computation, was that the middlewares that were being used in cyber-physical systems to provide abstraction and facilitate easy development for these systems, what kind of properties would one expect from these middlewares? And in this particular talk, I'm just going to focus on two properties, which is testability and security. So testability, the way that we define it is given an initial state to the system and a set of inputs, there can only be one correct behavior for the system. So you can think of a unit test that you provide. In that unit test, you provide a set of inputs to your system. And the way that testability would manifest itself is no matter how many times you run your test, the output of the module that you're testing should always remain the same, no matter what. This is not an exhaustive way of verifying that the system is working as intended. Nonetheless, this is widely relied upon in the industry. The other would be that we want to have some basic level of security. So we want to be able to prevent attacks such as man-in-the-middle attacks, replay attacks, and time delay attacks. These properties are fundamental enough that you would expect some level of support from your middleware. But what we found was, at least the ones that are openly available, generally lack these properties. So the way that we approached kind of this discovery was we started with a very real and very modern application that relies on one of these distributed system middlewares. And that example is Autoware.Auto. So Autoware.Auto is an open source end-to-end autonomous driving software stack. And they had their 1.0 release back in last April. And in that release, the vehicle was capable of parking itself autonomously. So you would drop the vehicle at a spot in a parking lot, and you point it to a parking spot, and it can go and park itself. So we chose this application because it ticks many of what we were looking for. So it is using, of course, a middleware. In this particular case, it's using Robot Operating System version 2. But it's also a very sophisticated and very modern application. So here is a depiction of the abstract architecture of the 1.0 release of Autoware.Auto. And as you can see, it's quite complex. So still, the question that we have is, does this system have testability and security properties at the middleware level? So what I'm going to talk about next is, instead of focusing on this very complicated architecture, I want to just focus on a very simple sub-architecture of Autoware.Auto. And let's see if this very simple sub-architecture has the testability and security properties that I mentioned earlier. So this is basically two nodes involved in Autoware.Auto. One of them is the LGSVL interface, which is the vehicle interface, essentially. In our case, our vehicle is actually simulated in the LGSVL, now called SVL simulator. And we have a software component that provides sort of a gateway to that simulation. And then we have the brain of the operation essentially on the right, which is the behavior planner, which is in charge of coming up with trajectories for the vehicle to follow. And in this case, the vehicle interface is doing two things. So on the state report, it is reporting the state of the gear of the vehicle. So if the gear is forward, it's going to report forward to the behavior planner. If it switches to reverse, it's going to report to reverse. And in Autoware, it's just, at least in release 1.0, it's just as simple as that. It's either the vehicle is either in forward gear or in reverse gear. And on the vehicle kinetic state, among other things, the velocity of the vehicle is reported. So the way that the vehicle interface is implemented is that if the vehicle is in forward gear, it is supposed to report a positive velocity because it's expected that the vehicle is going to be moving forward. And if the vehicle is in a reverse gear, it's going to report a negative velocity. Okay, so with that, we can now talk about the properties that we were trying to see exist in this subarchitecture. And here's where the middleware actually plays a crucial role. So without actually looking inside these nodes and seeing the logic of them, can I generally say that the system is testable? And to answer that, I need to look at the guarantees that that middleware actually provides. So in this case, the only guarantee that a robot operating system provides is that point-to-point delivery of messages will always be in order. So what does that mean? So imagine I've created a very simple test case here. So in this test case, the LGSVL interface produces a forward gear, and then later it produces a reverse gear. And because of the inherent guarantee in a robot operating system, the behavior planner will always see this in order, meaning that it will always see that the vehicle was in forward gear, and then later it switched to reverse gear. So talking about testability, and I'll cover what I mean by being secure in a second, but talking about testability, as far as this test case goes, because there is an inherent guarantee in robot operating system, no matter how many times you run this test, under, of course, reasonable assumptions, that should be also mentioned, but no matter how many times you run this test, you will get the same behavior. However, let's make a more complicated test. So in this more complicated version of the test, the vehicle interface produces a forward gear, then a positive velocity, then a reverse gear, then a negative velocity. Okay, so now what is the behavior of the system? Well, it turns out when we ran this over 300,000 runs, about 99.8% of the time, the behavior is actually as expected. So what you expect is at the behavior planner, you see things in order. So you see that the vehicle was in forward gear, had a positive velocity, then later switched to reverse gear, and then had a negative velocity, which makes sense. However, what concerned us was that about 0.2% of the time, you could see something, you could see a state that really makes no sense. So, for example, I've highlighted one such scenario. So the order of events that are observed by the behavior planner are 1, 2, 4, 3. So if you look at them, if you follow them, 1 means that the vehicle is in forward gear, 2 means that it has a positive velocity, and then all of a sudden what the behavior planner would see is that now all of a sudden the vehicle has a negative velocity while still being in forward gear. So what should the behavior planner do actually here? Should it assume that there's been an accident, or there's a malfunction, or there's some corner case scenario? Well, in this case, it's just robot operating system being robot operating system. And again, the concerning thing is that we had to run this 300,000 times, and we tried to kind of change the period at which we run this test to try to mimic the period that you would use for sensors. And statistically speaking, if I had run this test 1,000 times, I would have not seen any errors. And so the problem here is that this kind of behavior not only interferes and kind of disables our ability to properly test the system, because the system is actually not testable. It also introduces some security flaws. So you can imagine that this system is very vulnerable to time delay attacks. So all you need to do is really hold on to gear messages and just release them. So even if everything is encrypted, all you need to do is just hold on to the gear messages and release them late. And that is going to then subsequently severely interfere with the logic of the behavior planner. So this is sort of the attack surface that is also introduced in robot operating system. So the good thing is that we do have an alternative solution, and our alternative solution is, of course, the Reactor model that came out of Edwards' group. And this, the Reactor model is has a lot of nice properties, and it's very interesting. So I would definitely encourage you to read the cited paper here. But I'm just going to laser focus on a particular aspect of the Reactor model that would actually resolve the errors that we were seeing. So in this case, I've replicated the architecture that we were looking at in Autoware under ROS in lingua franca. So let's talk about some of the concepts first. So the Reactor model is based on the concept of reactors, which are a descendant of actors with particularly interesting properties. So the properties that I want to cover is that reactors use discrete steps, and they use a semantic notion of time, also called logical time. And what that actually offers is a clear notion of simultaneity. Okay, so let's walk through this example. So in here, I have a timer that periodically, in this case with a period of 10 milliseconds, triggers a reaction. And that reaction is in charge of producing the test vector that I was showing you. So the thing about lingua franca is that reactions take zero logical time to execute. So any event produced by this reaction will have the same logical time as the timer. And what will happen is that the semantics of the Reactor model guarantees that because the state report and the vehicle kinematic state, both of them, if events are produced on these channels by the upstream reaction, then it is guaranteed in the Reactor model that the downstream reactions marked 1 and 2 in the behavior planner will be logically simultaneous. So the behavior planner is guaranteed to always see the state report and the vehicle kinematic state at the same logical time. Moreover, as you can see, the reactions are actually numbered. So there is 1 and 2. So in the Reactor model, you can actually give priorities to reactions. So actually reaction 1, if a state report and vehicle kinematic state have events at the same logical time, always reaction 1 executes before reaction 2. So always actually geared data will be seen before velocity data. And that is something that would prevent the kind of issues that we were seeing under ROS. So based on the Reactor model, there is this ongoing effort, as Edward covered, to develop a coordination language called lingua franca that enables you to use any of the existing target programming languages that we support to implement applications that conform to the semantics of the Reactor model. That is the task of the lingua franca model, lingua franca language. And this is a collaboration between an international team. And over the years, we've built quite a sophisticated pipeline of tooling that I would encourage you to check out. I will not go into too much detail about lingua franca in the interest of time. What I want to highlight is that at the time, there were the existing runtimes that we had, the existing implementations, runtime implementations for lingua franca that we had, were not capable of honoring the semantics of reactors in a distributed setting. And the application that we just discussed, the autonomous driving software, but also in general, applications that make use of middlewares are distributed. So what we needed was, we needed to make some extensions to the existing runtimes, in particular the C runtime, to enable basically the preservation of the semantic of the Reactor model in a distributed setting. So there is a whole laundry list of things that we needed to add to lingua franca, and this list is growing continuously, including things like we have now a nice integration with ROS, actually. So what you can do is you can bring your existing ROS application to lingua franca rather easily. And we actually enabled reactors. So reactors now have the capability of sending and receiving ROS message types. So the connection type that you would use is still a lingua franca connection type because we want determinism, but you can actually on that connection send ROS messages. But we also have integrations where you can build your lingua franca program on top of an existing ROS application. And I'll get that to that in a second. But I want to highlight one particular extension that we needed to make to lingua franca. And that is the fact that if you want to preserve the semantics of the Reactor model across distributed nodes, by the way, we call these distributed nodes federates, and we call our distributed execution framework federated execution, we need some sort of an external coordination layer. And so far, we've built two types of coordination layers based on existing established coordination models loosely. So one, we have the centralized coordination model, which Edward mentioned in his talk, that emphasizes consistency. And that is based on the high-level architecture, HLA. And that's basically, you have a third process, in our case, in a two-federate scenario that I've tried to depict here. You have a third process called the RTI, runtime infrastructure, that is in charge of coordinating the execution in a way that honors the semantics of reactors. We also have a decentralized coordination that is based on Google Spanner and Tides. Without going into too much details, this coordination mechanism depends on assumptions about underlying overheads in the execution times, in network delay, and in clock synchronization error between federates to try to coordinate in a manner that preserves the semantic of the Reactor model. So that is sort of our implementation, a very high-level overview of our implementation. What I'm excited to show you is that in order to prove that actually what we've implemented is effective and also easy to use, we actually took the entire autonomous driving software, Autoware.Auto, and ported it to lingua franca. And I'm going to show you a very brief demo. I'm not going to show you all of it because it's going to take a long time, but this is basically Autoware running. I'm trying to increase the quality. It's not cooperating with me at the moment, but I'm running a lingua franca program, and what I'm doing now is giving the vehicle a parking spot to go and park itself. So I'm going to skip ahead a little bit. Feel free, this is on YouTube, so feel free to have a look. And then the vehicle is driving itself. So I think this is my PC lagging. It actually doesn't lag, it actually runs pretty fine. It's just my PC is having a bit of a trouble playing this YouTube video. And then eventually the vehicle will go and park itself. Okay, so with our demo, we revisited the kind of the conditions that we saw in our motivation, and we tried to kind of measure the same error rate for inconsistencies that we measured under ROS. And what we found was, of course, our centralized coordination reduced the error rate to 0. Our decentralized coordination also, based on reasonably small assumptions and reasonable periods for production of data, actually produced also an error rate of 0. However, we also tried periods that are typically not expected from sensors, such as 100 microsecond, 1 nanosecond, things like that. And under those, in order to get the error rate down to 0, you would need to make really pessimistic assumptions. However, the distinction here is that all these errors that show up are actually detectable in lingua franca. So you can detect them and then counteract them in lingua franca, versus in robot operating system in ROS, there is really no way to easily detect these, except if you want to add extra logic to your application. So just as one last note, so we also made comparison in terms of end-to-end latency between ROS version of Autoware and our centralized and decentralized coordinators. And we found that even though the centralized coordinator reduces the error rate to 0, the overhead on the end-to-end latency is actually quite high. So you can see the blue line here compared to the white line, which is ROS. The end-to-end latency is quite high. But we found that our decentralized coordinator is reasonably close to the ROS version of Autoware, but we had some actually interesting insights. So to just kind of go over them quickly, you can see that the ROS version of Autoware is showing two sets of latency measurements. One is around 100 milliseconds, one is around 67 milliseconds. And the way that this particular end-to-end latency works is we're measuring the end-to-end latency of a particular pipeline in Autoware. And as it turns out, the sensor that is driving this pipeline is the GPS, which has basically a frequency of 30 hertz. So the data for the GPS is actually produced every 33 milliseconds. And under ROS, sometimes that pipeline takes two data from the GPS sensor to produce an output, sometimes 3. So it actually non-deterministically switches between pipelines. But under lingua franca, that pipeline is always deterministic. Hence, we always get the 100 millisecond. But also, I want to emphasize that because of the determinism that we kind of have this weird projection in terms of execution times end-to-end latencies. And that is because a higher priority task is being executed, especially at the beginning of the autonomous valet parking. And that is showing up in terms of latency in lingua franca, but in ROS, because of its non-deterministic model of computation, actually there is no priority. So these kind of tasks actually don't interfere with each other. So that's why we believe there is a projection. But with that, that concludes my talk. And I think I ran a little bit over time.